All right, folks. Yesterday we were talking about the function f of x equals a to the x, an exponential function in which the variable is in the exponent. Okay. What I want you guys to kind of commit to is, yes, a to the x is fine, but I'm going to predominantly use that as our parent function or general form for a exponential, mainly for the fact that b could be a scalar multiplier, much like if I was working with some quadratic and we put like a quadratic into like vertex form, if you remember, x minus h squared plus k. Okay, but we always had an a out here. Okay, so that a right there is kind of like this b out here that we can stretch it vertically essentially. Okay, and what I want you guys to understand here is if we take a function like y equals 2 to the x, which we talked about yesterday being that curve there, and I compare that to y equals 3 times 2 to the x, what is happening here is because of that scalar multiplier out in front, because of that 3 right there, it's taking a point like 0, 1 on this purple curve, and it's taking the y value, and it's increasing it by a multiple of 3. So that becomes 1, 3. Does that make sense? Or 0, 3. Okay. This point here, which is at 1, 2, if I take that y value and scale it by a factor of 3, it becomes that point right there, which is 1, 6. So we can see the comparison between those y values. Does that make sense? Okay. So that point corresponds to that one. If I go out here to like 2, 4, okay, then when I scale that, I should have a 2, 12 on the other one. Is that doable? That's what that 3 out front is doing. Now, every year I get somebody to ask this or to do this, and they'll say, oh, well, 3 times 2 is 6. So I'm just going to write this as 6 to the x. Is 6 to the x the same thing as the 3 times 2 to the x curve? No. Okay. Anybody know why those are different? Anybody want to argue why I can't take 3 times 2 to the x and rewrite it as 6 to the x? Good. So laws of exponents say that you have to do that first when evaluating. Okay. So if I put x to be in like 3, then you go 2 to the third first. Then you evaluate that, make it 8 first, and then multiply by 3 to get 24. Down at the bottom, if I have 6 to the third, okay, that's just going to be 216 right off the bat. Does that make sense? Okay. So that gets us hopefully into being able to determine some equations from looking at these functions. Okay. Just like everything else when we talk about quadratics, we learn what the quadratic form is, and then I give you an image, a graph with some information in it, and you take that image, that information, and change it into an algebraic expression. We're going to do the same thing here. Okay. The only thing that you got to be cautious of is sometimes the information that they want you to use or that you need to use is not explicit. This, I think, is explicit. You're probably going to have to use that number or that ordered pair. This one here is not explicit. You're going to need to use that ordered pair of 0, 1. Okay? You're going to need at least 2 points that exist on your exponential curve to create the equation for it. One of those points, hopefully, is the y-intercept. Okay, that's going to be the easiest for us when we're trying to write these exponential curves. So every exponential curve is going to be of the form y equals some scalar multiplier b times a to the x. Okay, And because there's two variables here that we do not know B and we do not know A, there's going to be two iterations of substitution that's going to help us solve for B and A. The easiest substitution is going to be to solve for B first, and that's going to be by using your y-intercept. If you can use your y-intercept, that's going to make this process so much easier, because that is an x value and that is a y value, right? If I plug those in, so y is 1, B I don't know, A I don't know, but x is 0. And what that does is creatively destroys that A, doesn't it? What's A to the 0? 1. Okay? So by using that y-intercept, it allows us to get this to be B times 1, or just, in this case, B. So does that tell me what my B, what my scalar multiplier is? Does that make sense to everybody? Okay. Once I have B, then the second iteration of substitution is to go back to the original. Y equals B times A to the x. I already know B, so I'm going to put 1 in. Okay. Now I need another point. I can't use the same 0, 1 because that's just going to yield the same information. So I need a second point on my curve. My second point is 2, 25. So x is 2 and y is 25. So that gives me 25 is equal to a squared, right? So I square root, and what's a going to be? Okay, I agree it's 5. I'm going to initially put plus or minus 5, but let's go back up to here to what we said about exponential functions. Your a term has to be positive. Okay? Now the b could be negative. Okay, but the a value has got to be positive. So that's why when we do these, if we have to take an even root, we ignore the negative one. Okay, so we're just getting positive 5 here. So now my graph would be y equals, my equation of this graph would be y equals b, which was 1, times a, which we just said was 5, raised then to the x power. That is the equation that is going to yield that curve that is exponential, that contains the point 0, 1, and contains the point 2, 25. Yes?
So the bigger y just would be like your scalar multiplier, so it's like 0, 10, you would have instantly bigger multiplier of 10.
And if you can't use your y-intercept, then it gets a little bit messier, but you should be able to still do similar things, but it won't be able to see just from the order pair with the scalar multipliers. Now, I don't need to, when you write this, you don't necessarily need to write that 1, right? Multiplication by 1 is understood. Okay, so you don't need to write that if you don't want to. Let's go to this next one. Okay, again, ordered pair. Right there is 0, 1. So we're going to y equals b times a to the x. Y is 1. B I don't know. A I don't know. X is 0. So again, that helps us eliminate that a. It goes away. A to the 0 is 1. So that gives me 1 equals b. Take that information, start over, replacing b with 1. And now my y, so now I'm going to use this point. My y is 1/8. B is 1a, I don't know, but x is 3. So it's a little bit different than the last one. Last one we took a square root. What do we have to do here to solve for a? Cube root. So what's the cube root of 1? 1, what's the cube root of 8? 2. So then I get y equals b, which was 1, times 1/2 raised to the x. It is imperative that when you have a value that is fraction, or is a fraction, that you put parentheses around it. Because if I write it just like this, if I just write y equals 1/2 to the x like that, there's going to be misunderstanding of what that x gets attached to. Is it getting attached just to the 1? Is it attached to the 1/2? How does it? But with parentheses, I know that it is getting attached to the 1/2. Okay, so somebody might also, because of what we talked about yesterday, if can we rewrite this and say, can I distribute that x and say y equals 1 times 1 to the x over 2 to the x? Is that okay? What's 1 to the x? It's always going to be 1, right? No matter what x is, that's always going to be 1. So I have 1 over 2 to the x. And we could rewrite that as 2 to the negative x, couldn't we? So that and that, and if you want to put a 1 out in front of this 2, you can as well. But those two things circled are actually the exact same thing. So either one of those is acceptable. Okay. And that's just through a little bit of work with our laws of exponents. Cool with that? There's a third one on here. Why don't you guys take a minute and see what you come up with on that third one on your own. All right, so for the first one, y equals b times a dx makes sense to solve for b first. So I'm going to put y to be 2, b I don't know, a I don't know, but x is 0. So that wipes away the a. Did you guys get b to be 2? And that's what you said earlier, Jimin, right? Is that if I see that y-intercept is 0, then that right there is going to be my scalar multiplier, right? That's fine, okay? Then y equals b times a dx again, but now knowing that b is 2, plugging in that point. X and y to be 1 and 6 respectively, so 6, 2 times a to the first. I like when we get a to the first, or an x is a 1, because now this result is a linear equation to solve. So this equation to solve for a might be linear, might be quadratic, might be cubic, might be quartic, just depends on what that coordinate right there is. But now a, did you guys get 3? So then rewriting this whole thing, y equals b times a dx. B was 2, a was 3, raise it to the x. There's my formula, 2 times 3 dx. Can I write that as 6 to the x? No. Okay. Order of operations does not allow that. Do we understand exponentials a little bit? Understand, have a little bit of a fundamental foundation of them. I want to, and this is going to happen over the next couple days, actually start talking about applications of them. Okay? And I think, and just my personal opinion, and a lot of your pre-calculus textbook authors will be in agreement with this, that perhaps the most important application to you as a student is this with regards to finance. Okay? Exponential functions are used in stocks, in amortizations of home loans or mortgages, same thing with car loans. So, and finances, which is going to be one of the main things that we kind of devote our attention to as we leave high school and college, and that we want to have a good understanding of, is using exponential functions. Okay, so finances use exponential functions a great deal. And it's because exponential functions, we talk about exponential growth. Okay, and exponential growth is the growth of a population. And in this case, the population is just dollars. Does that make sense? Okay, we talk about the growth of cells. We talk about the growth of isotopes or decay of isotopes. In this case, we talk about the growth or decay of dollars. So one of the things that we're interested in is what was called compound interest. Okay, do you guys know what interest is, correct? Okay, simple interest just means if I have $1,000 and I invest it in a some type of account that has a 20% interest, simple interest says that I'm going to make $200 off that $1,000 invested. Okay, simple interest though says so if I leave it in there, I leave that $1,000 in there for another iteration to accumulate interest. Simple interest just says you're going to make only money off that original $1,000. Okay, so if let's say that we call it compound. Let's say I compound it once and I get $200. If I keep it in simple interest, then the next year or the next duration of time, I'm only going to make interest off that original $1,000. I'm only going to make another $200. Does that make sense? Compound interest is a little bit different. Okay, it's a little bit more complex. Basically what compound interest is, and I'm going to read this to you so I don't confuse you at all. But it says compound interest arises when interest is added to the principal. Okay, and then from that moment on, the interest has been added, also earns interest. Okay, so for instance, if I have, let's say we have an account, we put $1,000 in it with an initial principal of 20%. Okay, if you ever find an account that has an interest of 20%, come find me and we'll go rob everybody that we know and we'll invest it all in that account. Okay, because that is ridiculous. Okay, so I like a lot of savings. Anybody have like a savings account, trading account? Every year, you'll get a statement from your bank, usually about this time of year, telling you what interest you made off that account. And like every year, like I get one that says like I made like $1.38. Okay, so that's a very, very, very small. Not that I have huge amounts of cash in there, but it's a very small interest rate that banks give you for savings accounts. Money market account. You ever heard of money market account? Money market accounts are like 2%, 2.5%. Stocks higher, and certain stocks have different returns and that kind of thing. But 20% is pretty substantial. But if I put $1,000 in and I let it sit there for a year at a 20% interest, then after 1 year, I'm going to have $1,200, right? Does that make sense? Okay. So the idea is, what if I leave it in there longer? What if I go through this entire process again for a second year? I want that $200 that I made to actually be applied to or have the interest applied to that $200 in the second year. Does that make sense? Instead of just back to the original 1,000. So basically what happens is the idea, you can visualize it this way. Day one, I put in $1,000. I wait 365 days, and it turns into $1,200. Withdraw that $1,200. Now put that $1,200 back in the same account that has 20% interest, and that's your new principal. And now in the second year, instead of $1,000 creating interest, $1,200 is creating interest. So now in that second year, I make $240 instead of the $200 I made in the first year. Does that make sense? Okay. And at the end of the second year, I take out that $1,440 now that I have, take it out, put it back in, and then let that 20, so that's my new principal, and let that 20% attack that $1,440 instead of just the original 1,000. Does that make sense? So that's compound interest. Now, with compound interest, we can do it. We can compound it annually, okay, once a year. We can do it semi-annually, twice a year. We can do it monthly. We can do it quarterly. We can do it daily. We can do it hourly. We can do it instantaneously. We'll get into all that kind of stuff later on. But that's the idea of what compound interest is. Basically, the money that you made off of interest will then also eventually gain interest. Is everyone okay with that? Okay. What do banks do with your money when you put it in there? Okay, they loan it out. And when they loan it out, they attach an interest rate to it, right? So they might loan out $1,000 of your money, but the person they're loaning out to might have let's say they have an interest rate of 10%. So they loaned you your $1,000 out, but that person's going to pay back $1,100, right? So the bank's going to make $100 off that, right? They also take that money and invest it. Okay, put it in stocks, put it in funds, and all that kind of stuff. So that's how. So banks are, and this is understand. Like banks aren't. They're not like Good Samaritan, like doing good service duty for civilians, right? They are a business. Does that make sense? Same thing with we talked about this in geometry. Hospitals. Okay, they obviously they do good things for people, right? But what is their number one function? They are a business, okay? So always think about those things especially when you're doing finance and understanding that, you know, if I'm going to have a financial advisor or something like that, they're not just some really nice, your dad financial advisor? You do that stuff?
Yeah, a little bit.
He's a nice guy. But he's not doing that stuff all for nothing, right? I mean, he's got an invested interest in it. So you have to think about those things, that they're business people. They're trying to make money off you. Now, they have a fiduciary clause that says they have to do business that is in the best interest of their client. But you can't just say, I'm going to go to Edward Jones or Mr. Walsh's business and say, hey, take my money and do what you see fit with it. Because that's not really intelligent, right?
Yeah.
Okay, so you want to have a little bit of understanding of what is being done with your money and how that money is being accrued. Okay, so how does this get into exponential functions? I want to work a little bit with just some algebra 1 type stuff here, but it gets kind of messy on why this is exponential. So it says exponential functions occur in calculated compound interest. So there's an amount of money, P, called the principal, okay? If the principal is that's the initial amount that I put in. So that's the $1,000 that we put in at the beginning, okay? If it's invested at an interest rate, which we call I, per a time period, says then after one time period, the interest is P times I. Does that make sense? So if my interest rate was 20%, P times I is 1,000 times 20%, which is $200. So PI would be $200. Then the amount in my account would be P plus PI. Would you guys agree with that? It would have been the original $1,000 plus the new $200 that I made. Is that okay with everybody? Now they both have the principal in them, so we can factor that P out and we get P times the quantity 1 plus I. Okay? So now, what's going to happen? And this is where it gets kind of fuzzy. Try to make sure we understand this. It says if the interest is then reinvested. So now it's that idea that you don't really do this, but I think it gives a better visual that after that 1 year, I take this money out, I take that $1,200 out, and then I put it back in. I reinvest it, and that becomes my new principal. So this here in the second year, that becomes the new P value. Does that make sense? Okay. So we see this formula right here start to generate. And I want to show you, I'll explain to you how that arises. Okay. So we got this over here. Okay. So if I have 0 compounds, so that basically means day 1, I put my principal in. I put capital P in. Okay. After the first compound, after the first, let's just say in this case, the first year, the amount that I've made would be P plus PI. My original principal plus the amount made off of that principal. Okay? We can factor that P out if we want to. Okay? Year 2, what happens is that this now is what got reinvested as my principal. Does that make sense? So this P right here is actually going to become this down here. So this is my original, in year 3, this is the original amount that I'm putting in. So going back to our scenario, it'd be like that 1440. That's what's going in right here. Okay? Plus then, the interest times that number. Does that make sense? And that will tell me what I'll have at the end of the third year. So this is at the end of the third year. Okay? Now, what happens is I've got all these ors on the right-hand side of different ways that you can algebraically kind of finagle this. If I have P plus PI plus P plus PI times I, can I factor out, if I look at this as one term and look at that as one term, do they both have P plus PI in them? Does that make sense? So if I divide this by P plus PI and I divide this by P plus PI, there's my quotient. Or that's what I divide, that's my divisor, sorry. And that would be my quotient. Divide this by P plus PI gives me 1. Divide this by P plus PI gives me I, right? So this thing here can better be written as that, right? Does that make sense? Does this still have, both terms have a P in it? Okay. Take that P out and you get down to this, right? Is that the same thing as P plus 1 plus I squared? And we just got an exponential, right? And that squared refers to the second compound. Okay, so if I do this a third time, it gets messier. Okay. Basically what we do is we take this, and it becomes essentially that thing there. Then we go plus that again, times I. And we go through all this algebra, but we're going to find out after we go through all that algebra, it simplifies down to P times 1 plus I cubed. If I do it a fourth time, what do you think it's going to turn out to be? P plus 1, or times 1 plus I to the fourth, right? If I do it K times, this is usually what we say, it's going to turn into this formula right here. P, your principal, times 1 plus I to the K. Okay? Now, K is the number, so this formula is going to change a little bit. K is the number of times that you're going to compound for the duration of the time that your money is in the account. Okay? Interest rate, okay, we're going to introduce some new vocabulary here, or new terms. Interest rate is R, okay? And N is the number of times that you're going to compound it per year. The idea here, we'll go back to that last question we did with 20% interest rate. I'm going to get that 20% if I go through the entire year and I compound on the 365th day. Okay? I'm going to get 20% attached to that $1,000. If we compound, let's say, semi-annually, we go 6 months and we compound. Okay? What's going to happen at that 6-month mark is that I'm not going to get that full 20%. That first 6 months, I'm only going to get 10%. Does that make sense? So it's going to take $1,000, multiply it by 10%. Okay, it gives me $100, right? So then, for the second 6 months, instead of my original $1,000 being the money that is creating interest, or generating interest, now it's going to be $1,100 creating interest for that second month. And that second month of that $1,100 is only going to accrue a 10% interest. Does that make sense? Okay. So when they say an annual interest rate of 20%, if I'm compounding it monthly, I'm not getting 20% every month. I'm getting 1/12 of 20% every month. Does that make sense? Okay. So that's where we get this I here, your interest, okay, to be R divided by N. It's your rate divided by how many times you're going to compound it. Okay, and we'll do an example here in a minute, makes that maybe seem a little bit clearer. And N times T is the time period in T years. Okay, so this leads to the following formula. Okay, the amount at time T, or you value it at time T, is equal to your principal times 1 plus R over N raised to the NT. And that's exactly the same as P times 1 plus I raised to K, but we redefine what I is, it's R divided by N now, and we redefine K to be N times T. Okay? N times T is ultimately the total number of times that things are going to get compounded for the duration that you leave your money in this account. Is that okay? All right. Now, what we come across are some questions that they're going to ask one question, but it seems like it's really 4, 5, 6, sometimes more than that. Okay, so we get to a web assignment, I'll ask one of these questions, and it might have like 6, 7, 8 boxes to fill things in. I'm going to try to show you how you can kind of minimize the time spent on these problems by using our technology. But the idea here says a sum of $1,000 invested at an interest rate of $12 per year. Sorry, 12% per year. 12% per year. So find the amounts in the account after 3 years if interest is compounded annually, semi-annually, quarterly, monthly, and daily. Okay. The only thing that people struggle with in the past is realizing what annual, semi-annually, what that quantifies as. So annual is 1, Semi-annual is 2, quarterly 4, monthly 12, daily 365. Okay, those are the most common, frequently used. Sometimes they say weekly. What would be weekly? 52. Sometimes they'll say bi-weekly, which would be 26. Okay. So bi-weekly or biannually means that it's going to be every 2. If there's ever one that we come across that is not kind of common knowledge, I will provide you what it quantifies as. But weekly is 52. Okay. So this scenario says a sum is invested at $100. So P, my principal, is $1,000. I said 100, but it should be 1,000. So principal is $1,000. Okay. Interest rate, that's R, your interest rate. Now, this is the number one error that people make. Interest rate has to be a decimal. Okay, so a lot of people put 12 in. It's got to be 0.12. In the number of times that you're going to compound it, this is where it's really 5 questions here. Because you're going to see what is it when it's 1? What is it when it's 2? What is it when it's 4? What is it when it's 12? And what is it 365? Okay? And we'll talk about how we can kind of expedite that here in a minute. T is the number of years that you're going to have this money in the account. And in our problem, it says after 3 years. So T is 3. Okay? So every problem that you do of compound interest, those are the 4 things that you're going to write down. Then it's just a matter of plugging them in to this formula, 1 plus R over N raised to the NT. So A of T is my principal. So 1,000. 1 plus R, which is 0.12, divided by N, which in this case I'm going to just say is 1. We'll do this first one here. And then raised to the NT, which would be 1 times 3. Now, you can type that into your TIA 384, TI 30, whatever calculator you're using. I didn't mean to throw that. And then you can go on to the next part where everything changes to a 2. And that will require you on one of those calculators to actually retype everything again. Okay? Even if you know some of the functions, the recall functions on that calculator, on the TIA 384, it's still a little time consuming to hit like second enter and go back and insert and edit and all that kind of stuff. So what I want to show you is how we can do this with Desmos, and it becomes very easy. And we can get these 5 answers very quickly. Okay? So what you're going to do in Desmos, you're going to write one of these, you're going to write that formula. You're going to write P 1 plus R divided by N raised to the NT. And what's nice about it is it uses that math type, and I can know exactly that I've got my R over N correct, I've got my N to the T correct. What happens on TIA 3 or 4 is that when I have to hit that exponent N times T, I gotta make sure N times T is in parentheses. So people mess that stuff up as well. Desmos, I can't mess that up. Now, what I'm going to do is I just have to go through and define what I want my variables to be. So I'm going to say P. We said P was going to be 1,000. R, we said type in R, hit equals, and it's got to be 0.12. N, we said, in this case, was going to be 1. And then T was going to be 3. And once I fill all those in, you see that it automatically attaches those inside this formula and generates the output. Okay, so after 1 year here, or sorry, after 3 years, compounding once every year, so it's a total of 3 compounds, okay, you're going to make, you're going to have 1404.93 in your account. So you made $404, $405. Does it make sense? Okay. Now, the idea is, okay, well, that was just compounding like on December 31st of every year, right? Okay. Well, what if we did it, what's the 6 month, June. What if we did it June 30th and then December 31st every year? What would that look like? So that means that N would have to be 2. So I'm going to change N to 2. And instead of having to retype everything in, I just deleted 1 for N, type 2. It automatically generates that, right? So semi-annually, you get 1418.52. So if I had a choice, if Bank 1 and Bank 2 are offering me the exact same rate, but Bank 2 is offering me to compound it twice, and Bank 1 is only offering to compound it once, I go with Bank 2, right? I get 14 more bucks, 15 more bucks, okay? And that's only on $1,000. So if I had $1 million in there, that's even more, right? It's all relative, but it's, you might think, well, 14 bucks not that big of a deal. Well, what if your initial deposit was $1 million? Okay, then let's see what that would look like. If my initial deposit was $1 million. Okay, so 18, so it'd be 18,000 compared to 1. So I'd be looking at $15,000 there, right? That's a little bit more of a chunk, but it's relative to $1 million. If I have $1 million, maybe 14,000 is not a big deal. The next one says, what if we have quarterly? So quarterly means that we're going to do it every 3 months, compound every 3 months. So that's 4 times a year, and I make $14.25. So what are you seeing happen as the more compounds get applied? What happens to this amount? It's doing what? Increasing. If I go monthly, it's $14.30. If I go daily, it's $14.33. Okay, so I had at 12, it was $14.30. 12 compounds is $14.30. Okay, and then I did 365 compounds, so 350 some odd more compounds, and it only increased $3, right? Okay. Well, we can do more compounds though. Let's say we compound it twice a day. Okay, did I really make a whole lot more money compounding it twice a day, every 6 hours, or sorry, every 12 hours, than I did if I just compound it every 24 hours? I went from, that's 0.24 there as a decimal to 0.28. I made 4 more cents by compounding every 12 hours instead of every 24 hours, right? Well, what if I compound it every hour? Just multiply this by 24. Did I make that much more money? Compounding it twice a day, so every 12 hours, get 28. Compound it every hour, it's 0.32. I made 4 more cents. Okay. What if I compound it not every hour, but every minute? Do I make that much more money? It was 0.32 when I did it every hour. It's 0.32 now when I do it every minute, right? What if I do it every second? Multiply by 60 then. It's still increasing. And we're going to go with those decimals after that 9, 4, 1. So they're keeping growing, but not by a lot, right? Okay. So what happens here is we find out that as we start increasing further and further with our number of compounds, it starts to kind of tail off. Okay, our exponential growth starts to flatten off a little bit. Is this okay? Can we do this? All right. What I want you to understand is that if I am a consumer and I'm going to try to find the best deal for myself, if I'm choosing banks or something like that, I have to think about, what are they doing with my money? Okay, are they just going to let it sit there like it's sitting in a coffee can in my backyard? Or are they going to invest it, provide me an interest rate in a return? Are they going to compound it? Okay, so that my interest creates interest or not? Okay, those are all things and questions that you might want to ask or figure out before you make a decision on what you're going to do. There is an assignment, 4.1, open. Towards the end, there's going to be more questions like this, which we'll probably cover some more examples tomorrow. So I'm not going to make that assignment due until Friday. So we have more examples due or to go through tomorrow.